So hi, hello, and welcome to section number 5. Wow, thank you for being here. Now, I was out of town this weekend for a wedding, and because of that, I do not have my nice, neat section notes that are all like yossified and like pretty laid out like I normally do. So essentially, what I'm doing is I'm stealing some stuff from my summer version of this lesson on carboxylic acid derivatives, and it's really only one page of it. And then we're mostly going to be working on the section problems given that. So I don't have like a nice version that's posted on Canvas. If you would like, I can like send you the PDF of this like one page here that really is the only page that I have kind of that we're going to talk about or talk through a little bit. The big reason why is just with different teachers, there are like slightly different conventions for how to write things, and it's always a lot of editing work. Like for context, it normally takes me like 5 to 6 hours to edit each of my like section documents, and I just simply did not have time with the travel. So apologies for that. But yeah, I just wanted to start off by like touching base and checking in and seeing are there any kind of general questions or any things about studying, or how are y'all doing? Everyone's doing neutral. Will I eventually have the ossified version? That is such a great question. I think it will depend on how similar Lecture 6 is to the Lecture 6 I've given in the past. So if I can easily get back on the wagon with it and like do Section 6 and Section 5 like over the weekend, then yes, I'll have a Yossified version. But I definitely am going to prioritize getting Section 6 done so that like it'll keep going. So we will see. Need help studying? Girl, that's the one. Like studying organic chemistry when you get to reactions, I think is the challenge, full stop, period. And at the end of section, once we've worked through some problems, then maybe we can talk a little bit more about like study strategies and things. But the how to study organic chemistry reactions thing that we started last time in section 4, I think that kind of basis is going to be important to incorporate in of like the different ways of thinking about a reaction. Still adjusting, feeling a little discombobulated, keeping all the reactions straight. Yes. And 100%, like that is the challenge, and there will only be more reactions. And so doing some sort of like review sheet on your own, like remember for lecture 4, I had this little review sheet. I think you making one of those for each of these lectures, just to keep things organized, will be really, really essential and helpful. But yes, and then we'll also have office hours, or I'll have office hours right after this for like an hour, so feel free to like stick around and ask questions with homework and stuff. Cool. Well, here's the QR code for today with our little carboxylic acid, and I forget what the question is. It's also weird over the summer because over the summer the first exam goes through lectures 1 through 4, and so this section is like the day after the exam normally. So I think maybe the question is, how'd you feel about the first exam? Which, I'm curious how you felt about the first exam. Yeah, and then this is my favorite meme of the carboxylic acid derivatives, where you have carboxylic acid, ester, anhydride, amide, acid chloride, and then you have the nitrile as like the odd one out and the kind of odd cousin in this family. But all of lecture 5, essentially, was about this family of reactions using the carboxylic acid derivative functional groups. So these were the functional groups that were at oxidation level 3. So lecture 4 was this oxidation level 2 of aldehydes and ketones, and then this was lecture 5. And the big thing with lecture 5 is we want to know how to kind of interconvert between all of these different CADs, carboxylic acid derivatives. And that's what a lot of the reactions really focus on here. So there are a few kind of essential things to know about CADs, and this is my kind of like one-page summary of things. So the first thing that you definitely need to memorize and have down is the relative reactivity of the different carboxylic acid derivatives based on the functional group. This image is largely like adapted from lecture notes, at least for the summer lecture notes, where we can really rationalize why things are reactive or not by thinking about resonance. So, for example, like you see a carboxylate down here is the least reactive, and its resonance structure looks identical to it. So it has resonance structures that are equal and both really stable. There, it has full octets, it's putting the negative charge on an electronegative atom, like oxygen. Whereas over here, if we go up to the most reactive one, the acid chloride, when we do our resonance structure here, there are a few issues. Issue number one, we have a positive charge on a chlorine, which is a halogen and it's pretty electronegative, does not like that positive charge. Issue number two is chlorine is on the third row of the periodic table. It's a row down from carbon. So its p orbital here is going to be huge relative to carbon's p orbital. And so it's going to have really bad overlap. So like, yes, we would say that there is resonance here, but it's not good resonance. It's not resonance that's really stabilizing the molecule. And so that's why this has the worst resonance, so it's the most reactive. Then as we go down more and more, our resonance structures start getting better and better. Like eventually by the time we get to an amide, the amide places the positive charge on the nitrogen and the negative on the oxygen. And so comparing this, let's say to an ester, where we have a positive charge on the oxygen and a negative charge on the oxygen, who is happier with a positive charge? Or I shouldn't say happy. Who is less upset with a positive charge? An oxygen with positive or a nitrogen? Well, we think about electronegativities. So the nitrogen is going to be less electronegative, so it's more comfortable with that positive charge. And so this is a more stable resonance structure. The amide is less reactive. So going through each of these and really feeling like you can get a relative ranking of our functional groups of their reactivity, I think is going to be an important first step to see who are the players in this CAD reaction family in this game. So that's part one with CAD reactivity. Any questions here before we go on and talk about the CAD reactions themselves? / also, can I ask, is it still coming through like relatively clearly or is it being really choppy? Kind of hit or miss? Oh, not choppy. Okay. So like mid to neutral, something like that. Okay. Oh yeah, the background noise. I'm at a coffee shop again because of like traveling and stuff. So that's why it's not my home, which is normally quiet. Cool. Other things to think about are frontier molecular orbitals here with all of our CAD family reactions. And so one thing that we have is looking at all of the carbonyls over here. If we do our resonance structures, we know that this oxygen in the carbonyl has a negative charge in all of these resonance structures. And so we know that in the actual molecule, there's kind of a partial negative over here on all of these carbonyl oxygens. Now, because there's a little bit more negative charge on it, that is going to be our most basic atom, the carbonyl oxygen in all cases. Even when there are other lone pairs available, it's always going to be the carbonyl oxygen that is the most basic atom present. So let's say our reaction was happening in acid, and the first thing that you're going to do is protonate something. Well, you would protonate your most basic atom here, this oxygen. And this is like if H3O plus was protonating it. And then for our most acidic proton, it really depends on the molecule. And we're probably not going to talk much about this for removing hydrogens here. But noting that our HOMO is this lone pair on the carbonyl oxygen, and our LUMO is the pi star CO, that is pretty common to all of our CADs other than the nitrile, where with the nitrile's case, your LUMO is a pi star CN. So just because it's a carbon-nitrogen bond. Okay. So with this in mind, we can think about how we do reactions to get between all these different carboxylic acid derivatives. And the whole purpose of this family is just to interconvert between them, these oxidation level 3 functional groups. So this is the chart that I made for the summer version, and I think that y'all do a few more reactions than this, but the same idea still applies, the same principle, and I would recommend making your study chart for this lecture looking something similar to this. Like, some people really like the doing a chart. Like, I know Serenia normally does a big chart, but I really like this because there's a kind of big idea that structures how this chart is organized. It is organized so that the higher up the functional group is, the more reactive it is. So our most reactive is this acid chloride. Our least reactive of these is the nitrile, and carboxylate is not really listed because it's often not one that we are going to try to get as a final product. But if we did have it, it would be like way down here. But this is just kind of summarizing a lot of these reactions from lecture. And there are two key features that I want to kind of point out to be like the most important details about this family of reaction. So first important fact, everything can become a carboxylic acid. Carboxylic acid is our grand central station of the CADs. So if we are starting out with any functional group in this family, we can turn it into a carboxylic acid. Then our second key fact is it is easier to go down in reactivity than it is to go up. So if you are wanting to go from an acid chloride to an ester, you can do that in one step. If you're wanting to go from an acid chloride to an amide, also down in reactivity, you can do that in one step. However, if you wanted to go from an ester to an acid chloride, you do not have a way that you can do that in only one reaction. And it's because to go up in reactivity, like, it is a little bit harder. And so the strategy is, when you go up in reactivity, you need to first take it to the grand central station, to the carboxylic acid, and then from carboxylic acid, you can take it to the higher thing in energy. So typically it's going to be a two-step process to go up in reactivity, and typically it's only going to be one step to go down in reactivity. Now again, this is kind of a general trend, but I think it's helpful to have these like core ideas in mind as we start working on problems here, just to help keep it a little bit more organized. Now, I make a note here of you do need to know the mechanisms of these, but you're going to be using the line reactions a whole lot. And again, this goes back to the idea that I introduced in section 4 of you need to be able to work with these reactions at both the line reaction level of just predicting the products or writing reagents, and the level of mechanisms of full curved arrows. And the thing I want to warn you against is when we are doing line reaction problems, you should not be thinking about curved arrows. It will often take too much time and you're more likely to make mistakes. So we're going to get some practice with that, and when we do the line reactions and section problems together, we'll talk through a little bit of that strategy. The nice thing about these line reactions is if you look at the functional groups here, remember we talked about making a fake mechanism for like how to predict the product of a reaction. Here, the fake mechanisms are really easy. Typically, all you do is you chop off the thing on one side of the carbonyl and replace it with another functional group. So if you're going from acid chloride to an ester, you replace the Cl with an OR, where an OR is whatever alcohol that you use. So like, let's say if I used methanol, MEOH, to predict the product, I would chop this off, the Cl, and then in its place, I would put O, and then our R group here is methyl, Me. So that's at least the nice thing about this. Some of the transformations and like doing the line reaction level for the ketone and aldehyde reactions were a little bit trickier, especially with those hemiacetals. But these I think are a little bit more straightforward. And then the kind of core other like reaction things for when we talk about mechanism is all of the curved arrows for these reactions are very, very similar. The only types of arrow pushing that you are going to be doing are acid-base steps, protonations and deprotonations, doing a lone pair push to kick off a leaving group, and that looks like this, where we push down to form a carbonyl and kick off a leaving group. And then a nucleophile attacking a pi star electrophile, which is what this step is. Nucleophile attacking a pi star, and I should have a second arrow over here going up. So, with that in mind, the core reaction of all of this is you have some original CAD with some like special thing on the side. This could be our CL, it could be our OR, it could be an OH or whatever. A nucleophile is going to come up and attack it and push up. We get to a tetrahedral intermediate, and then we push down and kick off the old thing, and then we have our new functional group. This is the core theme, and then I think the harder part, the one that requires a little bit more thinking and nuance, is where we do our protonation steps if we're having an acid or base. So we'll get into that. But to start us off, I think that I'd like to start with the line reactions first, just to think about using this kind of like table moving down in reactivity or up in reactivity. So let's look at, this is question 2 and 3 from the section. Yeah, totally. Yeah. Mm-hmm. So with a ring, like if you had a ring over here, something like this, yeah, like maybe the thing I will say is like you don't know any reactions where the purpose is to break a ring. The purpose is always to go from one functional group to another, but then if the ring is involved in a functional group, then you might make or break a ring. So like for example, if you had something like this, which would be a hemiacetal, it is a ring. And so when you do a hemiacetal hydrolysis and turn it back into a carbonyl, you would break open the ring. But it's not because the point of the reaction is breaking open a ring. It's because that is how you disconnect a hemiacetal into its components. And your hemiacetal could be cyclic like this, in which case a ring is involved. Or it could be non-cyclic like this, in which case you're not breaking open a ring. So like whether or not we have a ring involved really depends on the specific identity of the products and like how that interacts with a functional group. So I think it would probably be easier to do that with like a specific example. And I'm trying to see if any of the questions that we have in the section handout today have a ring involved with it. And right. Cool. Yeah, no, great question, but it's sadly just not that general, you know? And then the other thing I'm realizing is I need to copy one more page from my summer section notes really quick, because there was one other little chunk of reactions. So we learned the oxidation reactions in lecture 4, and then we learned a few more reduction reactions here in lecture 5. And so, remember our oxidations were going from a lower oxidation level, like an alcohol over here, to a higher one, like an aldehyde or a carboxylic acid. And redox reactions, again, as a recap, are just moving up or down in oxidation level. And then the new ones that we used were to go from things at higher oxidation levels, like these carboxylic acid derivatives, and take them to things at lower oxidation levels, like here, alcohols and amines. So these are also a few other reactions that we want to keep in our arsenal as we start doing some problems. So with that in mind, let's go and look at some of the line reactions here. So, starting off with question 2, they've given us some line reactions that are tricky in that this is the version where they put the box over the starting materials. So they give us all the reagents, they give us the product, and we're having to predict what the original thing was. So what we have to do in this case is we have to analyze the functional groups in our product, and then we have to clock each of these reactions and be like, what are these reactions doing? Like, where did we learn this reaction? What was the goal of that reaction? So let's start off with our functional group analysis. What functional group do we have here in the product? Any ideas? Any thoughts? A ketone, ding dong. So we're actually not even in CAD land right now. Okay, that's fine. So we have a ketone. Then we have our last reaction. So we should always, like, this is the product, and this is the reaction immediately before making that product. So we should always work backwards when we go through these if we are trying to go back to our original starting material. If they had given you a structure here and then they want the product, then you would go in order of like 1, 2, 3 of all of these. Okay, so chromium. Where did we see chromium? What kind of reactions does chromium do? Well, chromium is our oxidizer. And so we know that this is going to move up in oxidation level. So the only reactions that we had that involved a chromium and ended with a ketone were ones that started with an alcohol. We would do like an ROH, and we would use chromium, and then we would have a carbonyl here. So let's think backwards, one step. And what I'm going to use is I'm going to use this kind of open arrow here, and this is called a retrosynthesis arrow. Basically, it is just meaning, hey, we are thinking backwards, whereas like this arrow means we're thinking forwards. So if we go back before reaction number 3, what our product looked like was, I'm going to abbreviate this benzene ring with a pH, and we had just an alcohol here. So we know that reaction 3, the chromium is going to take us from there to there. Great. Then I'm going to look back even further, and I see H3O+. Now H3O+, we don't know her as just a solo reactant for the most part. And so we're thinking about what other reactions are involved. And so I'm actually going to group these two reactions together, because we know this, with our MGBR, is our Grignard reaction. So our Grignard reaction is our MGBR with some sort of carbonyl, and it takes it to, we have added the R on, and then we have an OH where we had our alcohol. So if this is our general form for a Grignard reaction, well, it would make sense that the product of the Grignard is an alcohol. So we have that alcohol here. The thing that we still need to figure out is, what is our R group? What were the carbons that were added? And to figure that out, we can look at our Grignard reagents themselves. So over here, our Grignard reagent is ET-MGBR. So we know that we added an ethyl to our molecule. Well, where do we see a CH2CH3 that looks like it's an ethyl that could have been added to our carbonyl carbon? Like this carbon at the base of the OH, that's the one that would have been our carbonyl before. Well, it's not going to be cutting the OH, it's not going to be cutting the pH. If we cut here, do you see how when we kick that off, that gives us an ethyl? So what we had before we did our Grignard was we had that pH, but then we had a carbonyl here instead. And then we had the ET-MGBR. And that's these carbons over here. These were the ET. Now this looks a little funky here, but one thing that we can remember is we didn't draw it. This had a hydrogen here. If we know that this carbon has 4 bonds and we had an OH here, this still had a hydrogen. So this is not just a carbonyl, this is an aldehyde specifically. So that is going to be our starting molecule. Now, woof, we just did a lot of things all back to back to kind of work through this. And one thing that you will probably clock when we were talking through this is this thinking and doing this kind of work of working backwards with the actual structures is very hard to do when we don't have these core reactions already memorized. And like, again, it's hard to do when y'all have seen these reactions for truly like a week now, a week and a half, to internalize them and get to where you can think of these generic forms really quickly. But that is that skill that you want to be practicing when you're studying or making your flashcards so that this can come to mind really quickly. And then that allows you to actually work through the problem. But any questions on this one before we do the second one? It's going to be the same kind of process here. And maybe I'll also color this auction green. Okay. I will go on, and if there are questions that come up in the chat, I'll answer them. So then we have this. Okay, for the second question. What we're going to do is start again with the product functional groups. So what functional group do we have here? We have an amide. Very nice. So amide, as soon as you clock a carboxylic acid derivative functional group, you should be thinking, we're in lecture 5, I have my web of reactions. And then here we have MENH2 pyridine. Well, let me try to see where this could be in our product. Well, this nitrogen is probably this nitrogen, and that's one of the H's. And then this is probably the methyl, right? So we can imagine this is what got added by this last reaction, reaction number 2 here. Okay, well, if we are forming an amide, we know that we have to come from a functional group that is more reactive than an amide. So we could start with an ester, or we could start with an acid chloride, either one. So then, to help us kind of determine where we should start with that, like should this thing before be this acid chloride, or should it be some like OR? Let's look at this SOCl2. So SOCl2, thionyl chloride, how do you know it should be more reactive again? Because we know in the forward reaction, it's always going to be going down in energy unless it's coming from a carboxylic acid. So, like, the other thing is like an amide already is one of the lower energy functional groups here. Like if we look at our like little table, the amide's pretty low on our functional groups. And so the only things that can really form it are from an ester, an acid chloride, higher in reactivity, or carboxylic acid, because everything can interconvert with a carboxylic acid. So with that in mind, we know that we came from some other CAD functional group, and we have SOCl2 thionyl chloride, which is a really distinctive reagent. So let's go back to our table and see where do we see SOCl2. Well, we only have this as a reaction that starts with a carboxylic acid and forms an acid chloride. So if we are starting from a carboxylic acid and forming an acid chloride, let's keep that in mind, and we can finish this one out. So that makes me think that, oh, okay, after step 1, we are going to have a acid chloride. And before, we have a carboxylic acid. So that makes me think that actually this has to be an acid chloride when we're kind of thinking backwards through this. Because we know that that's going to be the product of the SOCl2. So then if we think backwards one more time, we know that it has to start with a carboxylic acid. So we're going to place that Cl with an OH. And that's how we get our initial starting material. And then once we have like preliminary like guess for what our starting material is, we can try to run through it. So this carboxylic acid, if we do SOCl2, we get this acid chloride. Okay. Then if we have an acid chloride and we add MENH2 and pyridine, then that's going down in reactivity, and that's going to form this amide. So it all checks out. Okay. Am I going too fast or too slow? Or how are y'all feeling? Because also I know that these are like baby's first line reactions in a lot of ways for like doing, now that you have, I don't know, like 15 to 20 reactions. And so it's a lot of kind of like putting all those pieces together. Where did the other H of MENH2 go? So during the course of the reaction, from an acid chloride to an amide, it loses one of the H's. It's something that's just deprotonated during the course of the reaction, but you can kind of see here. Here, I wrote it generally as like you have a nitrogen, you could have two R groups on it, and then a single H, and then during the course of the reaction, that one H is removed. And that's part of the mechanism of it. So again, working at the line reaction level, you don't need to know the why of why the hydrogen is removed, but at the mechanism level, if it was a mechanism question, then you would need to be able to kind of think through all of that. Okay. Let's look at 3 with these line reactions. So, first up, we have starting materials and products now, and we have to figure out the reagents. So our first step now is going to be analyzing the functional groups of starting materials and products together. So what do we call this bad boy, where it's like we have 2 esters that have been kind of glued together in the middle? It's not an ester, but she has a special name. An acid anhydride. Beautiful. Okay. And then what about this product over here? Well, we don't have a carbonyl, so we're not a CAD. We have a nitrogen. It feels a little bit weird, but this is just straight up an amine. Now, I'm going to teach you, or not teach you, I'm going to let you in on a little secret for our entire class. In the entire course, you will only learn 2 reactions that make amines as a product. And they were in this lecture. Those reactions were using lithium aluminum hydride to produce an amide, or using lithium aluminum hydride to produce a nitrile. And with our amine, if it's NH2 on the end, it could have come from either an amide or a nitrile. Because here, the big idea here is that this nitrogen on the end, when you're reducing it, has to form an NH2 if it's from a nitrile. It didn't have any other carbons or things on it. Versus our amide up here, when it gets reduced, you literally like reduce an amide the line reaction way by just erasing the carbonyl. So this nitrogen could be attached to multiple things, a bunch of different R groups. And so if our final product amine is anything other than NH2 on some carbons, then we know it has to have come from an amide. So, here, our amine. Do we have NH2 on it? No. So, if there's no NH2, we know that this came from an amide, because that is the only reaction we know. And it's a little bit cheating, because it's a little bit gaming the system of like, you haven't learned any other reactions to make amines. Plot twists, in the universe, there exist more reactions to make amines. Y'all will just never like see them. And so you can use that to your advantage of like, oh, if we only know one reaction that makes this type of amine, then we know we have done that one reaction. Now the question is, in our reduction of an amide to an amine, I'll write out the general form here. We have a carbonyl. We do lithium, aluminum hydride with ether and H3O plus. And literally we just erase the carbonyl. The question is, should our carbonyl go here, here, or here? Well, all of these are equal, right? They're all ethyls. So in that case, it just doesn't matter. Like, they're all the same. So let's just do our carbonyl here. And then I have nitrogen. And I could write out my ethyls like this. But just to save space, I'm going to write that as ET2. And that's this ethyl and this ethyl. Okay. So we know we had NET2 and amide. Okay. But what we started off with originally was an anhydride. So anhydride to amide, let's think, are we going up or down in reactivity? If we go from anhydride to amide, we know amide's one of our least reactive of the CADs. We are going down in energy, so we can do that in one step. So whenever we are trying to make an amide from something else, the reaction conditions are whatever the amine is, and then pyridine. So let's try to think about that over here. If we want this to have come from an anhydride that looks like this, we are essentially chopping here and swapping this like thing to the one right side, I guess, of the carbonyl. So we know that this right here, the thing that we've added, had to have come from the amine. So we have an anhydride and amine. Well, this is what we said earlier, and this goes back to the question about removing a hydrogen during the reaction. So if we add an amine and normally remove a hydrogen to form our amide, if we're thinking backwards, if we cut this off, we need to add a hydrogen on it to get the amine starting material version. So our amine is going to be HNET2. So with that, I think that we have our kind of general idea here. And I did a kind of working backwards. You could also do a working forwards. Generally, knowing which way to do like work backwards or forwards depends on what gives you the most clues. Here from an anhydride, you could hypothetically turn into a lot of different things. But because this amine was so specific, we know that there's only one way we could have made it. And that's why I was like, let's work backwards for this. So first off, going from our anhydride to our amide, we need our amine over here. So we do HNET2. And we need to throw in pyridine, a little base to help our reaction. Then that's going to be reaction 1 here, going from this to this. Then to go from our amide to our amine, we are doing our reduction. And so our heavy guns for doing reduction is lithium aluminum hydride, LiAlH4 with ether, followed by H3O plus. Ding dong, there we go. I think that's one of the harder ones here, so the other ones will be a little bit faster. Cool. Okay, moving on. Can anyone guess what the first question I'm going to ask of like, what is the first thing that we are going to do when approaching this line reaction? What's the first thing that we have done every time that we have done this? Does ether always go with LiAlH4? Yes, you're always going to have ether as a solvent for lithium hydride. Theodore, you're right on the money. Functional groups. So, can people throw out what functional groups we have here in starting materials or products? Functional group analysis. Ding dong. So, we have an alcohol. And over here, we have an ester. So we have an OR next to a carbonyl. It'll work. Okay. So now, ester. Ester is in CAD land, right? It's oxidation level 3. But this alcohol is oxidation level 1. And maybe instead of a number, I'll do ox level. So we need to go up in oxidation to get to CAD land. So who was our oxidizer? Who's doing that heavy lifting for us? Of course, it's our favorite, chromium trioxide, CrO3. Now, if we did chromium trioxide, CrO3, remember we have 2 versions of it. One version of it will stop at oxidation level 2, will stop at the ketone aldehyde level, and one version of it will stop at the carboxylic acid level. So who remembers what the sidekick is if we want to go all the way to oxidation level 3? We have 2 options, pyridine and water. So who do we need if we want to go all the way to oxidation level 3? H2O. Ding dong, thank you. So if we are going to a carboxylic acid, do you see how we have to add an oxygen here? Because we have to add an oxygen, we need an external source of oxygens, and that's going to be H2O here. So, okay, we know our first step is going to be oxidizing with CrO3 and H2O, and that's going to take us now to a carboxylic acid. And then we are just going from a carboxylic acid to an ester. So we can go back and refer to our little table. If we are going from a carboxylic acid to an ester, so from here to here, this is our Fischer esterification. So what we're going to use is we are going to use an alcohol that corresponds to whatever the carbon that's on the other side of the ester. And we're going to use an acid catalyst, an H+ catalyst. So let's think about this. And again, remember, we can use this cutting of the side here to help us out. This, if we cut our ester, our OR, that's going to correspond to the OR of our alcohol. And so all we need to do to get our actual alcohol is put an H on it. Okay. So, over here, I have my ester. I'm going to cut here, right next to the carbonyl, and kind of thinking backwards to what came before it, this would have come from a carboxylic acid and then an alcohol. And this is our OR, so I'm going to put an H on it now. And then our alcohol would be this. So this right here is methanol, MEOH, right? Because that's a CH3. So my second step is I'm going to add MEOH, that's our alcohol, and we need an acid catalyst. So you can just write H plus cat. I think the other way that they put in the class of writing it is you could write it as literally the protonated alcohol here, like you just add another hydrogen to the MEOH. But I think this looks cleaner, and like if you write this, everyone will know what you are talking about. And I think the answer key puts both of them, so. Cool. Last one here. So, we are going from an ester to an alcohol. Ester, alcohol. Then the thing that we are going to also be asking, and this is typically here with these lecture 4 and 5 reactions, a good check is like who is in the CAD family, who is not, and did we have to do any redox between this? Did we move up or down in oxidation level? Because within the CAD reactions, we're all staying at oxidation level 3, but we know that we can move in and out of the CAD family with redox reactions. So our ester is at oxidation level 3, and our alcohol is at oxidation level number 1. So we went down in reactivity, right? We did some sort of reduction. But let's say, hypothetically, we were to just do our like lithium aluminum hydride reduction. I'm not writing out the full reagents. If we reduce an ester, what happens is you cut off your OR group, and then you turn your carbonyl into an alcohol. So the product of that would look like this. That's if we use lithium aluminum hydride and did a reduction that way. How is this different from what the actual product that we get is? Well, it looks like there are two other little guys here. So over here, we have two methyls that have been added. So does anything ring a bell to you so far of if you're trying to add carbons to some sort of carbonyl, what reactions are coming to mind for how you add carbons to a carbonyl? Our Grignard, MGBR, exactly. So this is another thing where I am going to go back and pull another note from the summer version, which again, I wish I had had time to yossify and put it together in a nice, neat way, because you know how much joy it brings me. But we teach this reaction in lecture 4 in the summer, and so we do it in a slightly different order than the fall. If you do Grignards or like the lithium hydride adding to an ester, it's a little bit different than it adding to a ketone or aldehyde. So remember, our mechanism for adding to a ketone or aldehyde looks like this, where our R group went and attached the carbonyl, and then we protonated it and made it neutral, and we've added one R group. When we attack an ester, however, it starts off the same. Our carbon-metal bond, sigma bond, goes and attacks the carbonyl, pushes up. We've added an R group. But then, this is the thing that's different. When we had like a ketone or an aldehyde, we had these as carbon-carbon bonds or carbon-hydrogen bonds, and those are hard to break. Making and breaking carbon-carbon bonds will be a core theme and a challenge throughout the course. And so, anytime you make or break them, that is a notable reaction that you're going to want to kind of keep coming back to. But here, when we attacked this ester, this OBT is actually a pretty good leaving group. We can kick this off and it'll be relatively stable on its own, because when we kick it off, we have an oxygen with a negative charge. Versus imagine we tried to kick this off over here, we would have a carbon with a negative charge. Very angry, does not want to exist. No, she will not happen. But she can happen. You know, oxygen is good with a negative charge, it's electronegative. So here, because we have that good leaving group, we push down and we make a new carbonyl, but now this functional group is a ketone, and we still are in the presence of our Grignard reagent, our like carbon metal bond. And so a second equivalent will come along and attack it. So now we have two R groups added, and then we do that protonation step like we saw with the normal addition of a Grignard to a ketone or aldehyde. So this, we call it double addition to an ester, where when a Grignard organolithium or lithium hydride attack an ester, it's going to add twice instead of just adding once. So this should be kind of a pretty like immediate association to have in your mind as you are doing reactions going forward. It's very much like esters, double addition to esters. To the extent that like if you're at a coffee shop and they say, I have a hot latte ready for ester, you should think double addition to ester. Like it's all just like one of the immediate associations that you should kind of have with an ester, should be building with an ester. So given that, let's go back and look. We had an ester. We did a double addition of two methyls. So what do we need to do? We just need a Grignard, and it's going to add twice because we know that we have double addition to esters. So in this case, the things that we were adding were methyls. So I'm going to do methyl MGBR in ether. And then I'm going to do H3O plus as my second step. And then bada bing, we're done. No other reaction is needed. So, I don't know. This feels like a lot. Like, these feel like a step up in difficulty than the reaction things that you have seen before. What questions do people have? This also feels like my least instructive section so far, because so much of it is based on like working the problems and seeing the process of them now that we're in reactions. And so it's not going to be like walking through each of the mechanisms yet. Yeah, the digestion time for the new reactions is certainly very real. And like combining that with however you're like studying, yeah. Okay. Well, I'll give people a chance to type, but I will go ahead and start thinking about the next few reactions. So, also at the line reaction level, we have question 4. And question 4 looks scary. It is meant to intimidate you, but, you know, the Lord sends his toughest battles to his strongest soldiers, and here you are taking organic chemistry, so we can get through this. So, all of these molecules look kind of crazy. We have these like bridged rings. We have like a bunch of substituents on here. And really, what we are doing here is a watered down version of a synthesis problem. So in other, like for chemistry majors, they would give you the starting material and the product, and they wouldn't write any of this in the middle to help you. And they would just be like, do it. We are not going to do that to you. That's not a type of question that we ask in this class. But because that type of thinking is so prevalent within chemistry and is a big focus of chemistry, of building specific molecules, it's something that like informs a lot of how we teach y'all. And so you're going to see these kind of reaction schemes where essentially you can imagine them as just solo little line reactions. Like this is an isolated line reaction. This is an isolated line reaction. This is an isolated line reaction. And a synthesis or a synthesis framework like this just pieces them together. So the nice part is you can just take each one of these like missing pieces as like one at a time a separate question, which is really nice. The other thing that's nice with this is sometimes in true box problems, we'll have like 3 or sometimes even 4 steps on an arrow. Whereas when we do these kind of synthesis frameworks, we'll never have more than 2 steps on an arrow. So it breaks it up even a little bit easier than a normal reaction. So we approach this just like the line reactions. Let's start off with our functional groups. Over here we have a nitrile. So one thing to just keep in mind is nitrile we often write as CN, and that's C triple bond N. And actually I should make my bond angle linear. So that is our notation for a nitrile. And then we also have an alkene. But do we know any reactions of alkenes? No. So I'm just going to ignore her. And also she's there in the product, so we don't care. Okay, our nitrile is here. And then in the next one we have a carboxylic acid. And let's just count our carbons to be safe. So I'm going to call this corner carbon yellow. Then one carbon is green. And then the carbon in the nitrile becomes the carbon in the carboxylic acid. So, nitrile to carboxylic acid, both of them are in CAD land. So we can just go and look at our chart or table or whatever we are using to kind of guide our reactions. So, going from a nitrile to a carboxylic acid, all we need is H3O+. So, or you could do it in base and NaOH and then do an acid workup step. But it's easier to just do it in one step. So, H3O+. Okay. And already you can see each of these substeps are going to be faster than the big kind of line reaction questions that we did before. So now we are going from our carboxylic acid to an alcohol. Well, carboxylic acid to an alcohol, what types of questions should we be asking as we're doing that kind of functional group transformation? First question, are they both in CAD land? Well, carboxylic acid is, but alcohol is not. Second, if one of them's not in Cadland, we must have done some redox, right? So here we went from oxidation level of 3 to an oxidation level of 1. So we did a reduction. Who's our big reducing agent? Who goes down in oxidation level? Who is our reducing agent that goes down in reactivity from a carboxylic acid to an alcohol? That's so valid. That's so valid. Okay, y'all are on the right track. You truly are. So, this is why I like teaching the redox reactions together of the oxidation and the reduction, because the big boy player for reduction is lithium aluminum hydride. The big boy player for oxidation is chromium trioxide. Fallon, you're totally right. NaBH4 does reductions. But remember, we characterize NaBH4 as like soft boy, the like weaker version of reducing. So the notable thing about between these two, they both do reductions, but NaBH4 will only react with ketones and aldehydes, whereas lithium hydride reacts with ketones, aldehydes, esters, amides, a bunch of functional groups. So for the purpose of like lecture 5 CAD stuff, lithium hydride is going to be our go-to. Cool. So, let's go back over here. So, we are going down oxidation level, we're doing a reduction. Our main girl to go to is lithium aluminum hydride. So, we're going to do step 1, lithium aluminum hydride in ether. And step 2, H3O+. Now, notice when I'm doing this again for the line reaction level, I am not thinking through mechanisms. Like, not once have I thought about a single curved arrow. I have only thought about, like, okay, I'm going from this functional group to this functional group. What are the reagents I need? Just recalling the reagents. And that's a memorization thing, not a, like, conceptual think-through thing. The bigger thing for concepts right now is thinking through the process of, like, IDing functional groups. Did we do redox or not? Are we going up and down in CAD reactivity? Okay. So now we have an alcohol, and we have an acid chloride with pyridine. Interesting, interesting. Well, acid chloride is our most reactive CAD, right? And so we can go from acid chloride to an amide, to an ester, to a carboxylic acid. But if we are adding an alcohol, then that means that this O, I'm going to call this whole thing R, this OR needs to be added to the carbonyl. So with that in mind, we are going to replace the Cl with this whole OR nonsense. So I'm going to draw my big OR. So that's the OR bit. And now that's going to add to this carbonyl. And so the functional group we get out of it is an ester. Work. Now, the next step here, this is a reaction that y'all have not learned yet. You will learn it in, I think, lecture 8-ish, something like that. So we ignore her and we move on. And somehow that's going to bust open this ring. Very mysterious, very exciting. Then what we have is we are starting off with this thing, and whoa boy, functional group city. Someone like throw out a functional group that you see here. Feel free to put in the chat or to unmute and say. There are a few different functional groups that we see here. Ester, totally. We have an ester. And then, great, we have 2 carboxylic acids. Well, then our reagent is the bad boy reagent, thionyl chloride. And thionyl chloride only does one reaction that y'all know so far. Thionyl chloride takes carboxylic acids to acid chlorides and nothing else. So what we are going to do is we are going to take this whole big molecule, and anything that is not a carboxylic acid, we are not going to touch. So I am literally just drawing out things. Hydrogen. Okay, and now these carboxylic acids, I'm going to cut off the OHs and put chlorines in their place. Done. Again, line reactions so quick. Hopefully will become so easy. And the last thing that happens is they add an amine here, and it's going to react with these acid chlorides and turn them into amides. Because when we go from acid chlorides to amides, we go down in energy. Work. So we've done our first big synthesis framework. That's kind of a lot. So, I will pause for another minute for questions. Apologies if the pauses are a little bit annoying, but also I love y'all's questions and want to hear what you are thinking. If I was in your shoes and I was seeing this, I would feel overwhelmed. I don't know how y'all are feeling. But I'd be like, wow, you're asking us to do a lot very quickly in terms of being able to just work with these reactions. And part of it is when I am moving quickly through this, again, it's because I already have that memorized, locked and loaded. And so part of it with teaching you is I can show you the thought process, but being able to retrieve that information quickly of having it memorized is not something I can really do with you. It's going to be part of your studying and how that interacts with the course. And so oftentimes I think it is a really normal thing to be wow, this is going fast and I could not do this on my own. And I think making sure to clarify, is it I am feeling this way because I just don't have this memorized yet? That's option one. Or I feel this is going too fast because I don't know how or why something's happening. And I think just splitting that up is helpful as you are kind of studying and thinking through this. And if it's more the option two of I don't know why or how, then I think that's ask a question. How did we realize to do this? How did we know that it only reacts with carboxylic acid and not ester? Blah, blah, blah. But yeah, this is the part of organic chemistry that gets a little overwhelming. So I'm here. You can do it. Let's go from this and let's back up and go to question one, which is a mechanism question now. So in the mechanism, they want us to provide the reagents. So it's kind of like a line reaction first. And then they want us to do curved error as a full mechanism. So let's start off by treating this just like a line reaction question. We're looking at our functional groups, carboxylic acid to ester. And if we go back to our study notes, carboxylic acid to ester is a classic reaction. This is the most quintessential carboxylic acid derivative reaction. This is the Fischer esterification. I would be surprised if it did not appear in some form or fashion on an assessment, either the next midterm exam or the final. It is the probably most important CAD reaction to know. Just because it really puts a lot of things together with acid catalyzation and these acyl transfer reactions, which is the family of reactions that we're talking about. So basically, to go from carboxylic acid to ester, the reagents we use an H+ catalyst, and then we use an alcohol, and that alcohol needs to correspond to whatever this OR is. I think we've had another line reaction where we had to do ester, Fischer esterification. So let's find our ester, and let's cut. So over here we have this OR, and I'm going to put an H on it to make the alcohol version. This is ethanol. So our reagents that we need are ethanol and an H plus catalyst. Okay, we've done the line reaction portion. Are we ready to start the drama, mystery, and intrigue of doing our curved Euro mechanism? So, the first question to ask ourselves if we are doing a CAD mechanism is, are we in acid or are we in base? If we are in base, typically we are just going to straight up attack the carbonyl. And the reason that we can straight up attack the carbonyl in base is because in base we're typically going to have something with a negative charge, like an OR minus. OR minus, having a negative charge is making that a high energy nucleophile, a high energy donor. And so it's able to go and attack the carbonyl directly. So in base, it attacks the carbonyl directly. But in acid, the first thing that we are going to do is we are going to protonate the carbonyl. And our reason for doing this is it makes our electrophile, our accepting orbital, our LUMO, lower in energy when we protonate it. So remember, we're trying to have that LUMO and HOMO, and we are trying to lower the gap between it by either having a high energy donor or a low energy acceptor. So when we have H plus catalyst and ethanol over here in a solution, we are going to have ethanol, and the other thing that we are going to have is ethanol that's protonated like this. So that is the acid version of it, as if you've just added another hydrogen on it. It's kind of like how we go from H2O to H3O plus. We add another hydrogen on it, put a positive charge. And like this is kind of our H2O, and then we add a hydrogen on it and a plus to get our acid version. So if we are going to protonate this carboxylic acid, we need to think back to what is the most basic atom in this carbonyl. Well, it is going to be on the oxygen up here, because remember, with resonance, we said this was a partial minus, and this is a partial plus, because we have a resonance structure that pushes electrons towards this top oxygen. So, with that, our lone pair here is going to come and grab a hydrogen. And I'll try to do the curved arrows in red, just to make it stand out a little bit. So over here, we now have added a hydrogen onto this top oxygen, and it has a positive formal charge now. Now the other thing that we get out of it, and you don't always have to write it, but well, when we take a hydrogen off of protonated ethanol, we get just a normal ethanol, like this. Okay. Well, now, to do this reaction of going from a carboxylic acid to an ester, we know that this ethanol somehow has to get attached onto this carbon. We know that we have to get this oxygen attached to this carbon. And this is going to be our fundamental nucleophile and electrophile donor-acceptor pair. So we have a lone pair on the oxygen here, and that's going to be our lone pair on oxygen donor, and it's going to go into our pi star CO acceptor. So we are going to attack and push up. Work. So when we do that, we know electrons and antibonds make the bonds break. So we are not going to have a double bond anymore. We're going to have the base of the carbonyl stays the same because we didn't break either of those bonds. We're then only going to have one bond remaining over here to the OH. That was our carbonyl. So this is, I'll use kind of yellow here. This was our carbonyl. And then we have our ethanol attached now to this carbon. So like this is our central carbon. And then this is our oxygen from our ethanol. But now we see that this oxygen has 3 bonds associated with it now, so it's going to have a positive charge. Okay. Well, now, getting from this to this at the end, we somehow need to get off an OH. Like one of the OHs needs to leave. But also we see that here this OET is neutral, whereas here it's positively charged. So if we're thinking about kicking things off and we're thinking about like acid-base protonation, deprotonation, it's always going to be faster to do acid-base things. So this is where I think Serenia introduced this idea of a proton transfer. And a proton transfer is, right now, OH is not a good leaving group. And we said that like if we are in base, we could potentially kick off a negatively charged OH, but you will never kick off a negatively charged group in acid. So what we need to do is we need to think about, okay, let's make this top part neutral so it can stick around, and then let's protonate this, make it OH2 plus, so that it is a better leaving group. So if we are doing a deprotonation and a protonation together, we can call that a proton transfer, which I'll put right PT or proton transfer. And it's just because y'all are getting to the point where those curve steps you can do. Like we trust that you know how to show that. And this is an abbreviation that we will allow you to do even on exams. So all we are doing is we have deprotonated this top one and we've protonated the bottom one. Now, one thing to kind of keep in mind here is these hydrogen, like the second hydrogen that comes on over here, is not necessarily this hydrogen. It's not that this hydrogen is coming down and moving or something like that. It literally is just a abbreviation of what I'm about to show in green. So what would happen would be another equivalent of ethanol would come and deprotonate it. Then we would have here the deprotonated version, everything neutral. Then this OH would go and grab a hydrogen off of a protonated ethanol. And then that would take us here. So again, this hydrogen does not need to be the same as this hydrogen. Hydrogens are going to be flying on and off. But again, with this abbreviation, it's just having to be careful with knowing what that means and what it's representing. So now, to get from here to here, we are getting close. We have essentially packed the bags of this molecule to make it a better leaving group. And I kind of used this little metaphor for tetrahedral intermediates last time as like it's an apartment shared by 4 people. And here, when we protonate this H2O, or like protonate the OH to make it H2O plus, we have made it a really good leaving group. So if this is kicked off right now, it's water. Water is neutral, water is just vibing and chilling. And so, in our apartment metaphor, I likened this protonation step here as like packing the roommate's bags that you're about to throw out of the apartment. So, with this, what we are going to do is we know that we need to form a carbonyl, and this oxygen up top is going to be the oxygen that was in our alcohol. And we know it's that one and not the other one because we see the oxygen that's in our OR group, or OET, she's still a single bond. She's not a double bond product. So we are going to do our dramatic lone pair push, evicting her from the apartment. She said, "I don't like your face. I'm going to push down, kick off H2O." So when we do that, we are going to have... sorry, here we are. We are going to be making a double bond here because these electrons are going to be pushing down an N, and we have an O with an H. And now this oxygen has 3 bonds to it, so it's positively charged. And oh my goodness, we are so close. Going from here to here, we only need to do one more thing. But also I realized I didn't make these arrows red, so let me make them red really quick. Okay, so last step, all we have to do is a deprotonation. So another equivalent of our ethanol is going to come along, deprotonate here, and that gets us to our product. So woof, we got through it. Now, doing this full mechanism, the way that I talked through it with you, it's almost as if we were like discovering the mechanism for the first time of like how and why this might happen, which is like a very kind of conceptual way to approach it. And it's also assuming that y'all haven't memorized it. But like the way that you should be approaching it is this is a reaction that was taught in lecture. And so you should go through and memorize those steps of like inefficient esterification. I'll go ahead and do a little abbreviation. Step 1, you protonate your carbonyl. So that's what we did over here. Step 2, alcohol nucleophile attacks the carbonyl electrophile. So that's step 2. Step 3, you do a proton transfer. Step 4, lone pair push off the H2O. And maybe for the proton transfer, just to give a little extra info, I would say neutralize and make an OH2. So you kind of neutralize this one and turn one into OH2, or water. And last step, you do a deprotonate. And these are going to be the steps every time you do a Fischer esterification. If I change this carboxylic acid to being this molecule and I changed my alcohol to being this, it's going to do the exact same curved arrows in the exact same order. And so the thing to be memorizing is once you clock that's a Fischer esterification, these are the steps. And getting that super ingrained is going to take practice and everything. But then when you have this locked and loaded, you don't have to do all that deep thinking about each step. This deep thinking that we were doing and kind of analyzing it as we go is much more a tool to help y'all study as you are learning this for the first time. But this is where you should be going as you study and having that in mind. The other thing that I think is really helpful is after you do a mechanism, go back and do this sub-steps. Like this is your like mechanistic logic, where you number all of these steps and connect this to that general Fischer reaction. Okay, last thing, we have this quick little question 5 down here. Question 5 says, we can go from this alternate starting material. So normally in the one up top, they start off with a nitrile over here. They said that we can go from a bromine to this, carboxylic acid. Whew, okay, that looks a little difficult. Well, maybe to start off, oh wait, questions, love questions, yes. Okay, Fallon, do we need to be regenerating the ethanol again before we can use it, or does the idea of using regenerating only apply to catalysts? So, answering that question first, the idea of regenerating the catalyst is really only a conceptual thing for y'all, because for our purposes, this is in a beaker that has a ton of ethanol molecules. You are having moles and moles of ethanol. And you are also going to have the acid catalyst. You are going to have a protonation in there somewhere. You're probably not going to have as much of it. But one thing that we do see is like in the first step, we used up our acid catalyst, H3O plus, or the protonated ethanol. In our last step, we generate a protonated ethanol. And I didn't write that as another product, but we could write that just for completeness, that we get back out from this thing. And it goes kind of round and round. So that's question 1. Second question, why do we protonate the ethanol before the deprotonation? I think you mean why do we deprotonate the ethanol before we do the protonation? Why can't we just use floating H+ catalyst? Okay, so both great questions. So first of all, you do the deprotonation first, because if you did the protonation first, what you'd form is this. And this molecule has 2 positive charges on it, which is like just really unlikely to happen. Like it's very unstable. Having a molecule with a 2+ charge is like, eek, yikes. So that's kind of why you do the deprotonation first, so you don't have 2 charges on it at the same time. And then why can't you use floating H+ catalyst? So it's because H+ catalyst doesn't exist. You are never going to have just a free proton around. This is a convention for chemists to short and a like very quick way to write it. The thing that is going to be our acid is protonated ethanol. like the way that we would form this protonated ethanol is essentially we drop in probably a drop of hydrochloric acid. And here, this would go and grab a hydrogen from the hydrochloric acid, and then that would make this protonated ethanol, and then you'd have a Cl minus aqueous kind of floating in solution. So, like that's kind of why there's no H plus. This is just an abbreviation for us as chemists. And then for Gabby's question, step 1 to identify functional groups and determine if they are cat or not. Yes, for this, like generally speaking, first thing you should be doing is IDing functional groups, and then thinking about how those functional groups connect to the reaction families that you've learned so far. So for example, if you identified functional groups and you see a ketone, you should immediately be thinking in lecture 4 of the reactions of ketones, of what are all the different things I can turn it into, and things like that. So, yes, and then because this is on lecture 5, which is CADs, you should determine if they're CAD or not, then like kind of if there are redox reactions happening, and then going from there to kind of connect everything. But let me wrap up this last one before the office hours. So we are going from a alkyl halide to a carboxylic acid. Woof. I don't know any reactions that do that. So maybe let's use our ignorance to our advantage here. Y'all only really know 1 or 2 reactions that start with an alkyl halide. Can anyone think of a reaction that starts with an alkyl halide from either lectures 4 or 5? So a reaction that starts with an alkyl halide from lectures 4 or 5. Grignard, magnesium. So we know that we can do step 1, add elemental magnesium in ether, and that's going to make this into MgBr, which I should write this way because the Mg kind of inserts itself into things. And then we're going from a Grignard to this carboxylic acid. So this is kind of weird and tricky. But maybe to help us out, let's do some mapping. So this is our kind of corner carbon. Then we have grain carbon here. And the thing that's kind of funky is in our product, when we have the carboxylic acid, we also have an additional carbon. So we have an additional carbon here, whereas here we don't have a carbon yet. So this carbon needs to come from whatever was attacked. And the other thing about it is we have a carbon and we have a bunch of bonds to oxygens here, specifically 2 oxygens. So this is kind of a, like, not trick question, but like it's a very specific type of reaction. I think it was like at the bottom of a page in lecture. Like it wasn't emphasized to say like huge reaction, but we can have our Grignard go with ether and attack CO2. So that's going to be our first step, our Grignard, ether, and CO2. And then we can do an H3O plus, our like acid workup step. What that looks like is here we have CO2. Literally the carbon magnesium bond is going to go and attack one of the pi star COs, break it open, and then that's going to go to this is our carbon. We still have this double bond. I'll call this double bond here that stays around like that. And then we have O minus here was this bond. And then from here, our H3O plus, all we do is protonate it over here. So our alternate way of making it from this bromide is we start off with Mg and ether, then we have our Grignard reagent that we just made attack CO2 and do an acid workup. It's that easy. Wow. So again, this is a lot. I will go ahead and stop section recording and everything for now. But I'm about to have office hours. If you want to ask either about any of the things from section today, talk about studying, questions about the homework, I will be around for the next hour. So thank you all for showing up to section. I hope that this was helpful, and then I will start taking some questions. Thanks.